we ran out of time in the first session. It actually ended with some discussion questions that I wrote down. And it's sort of a mini quiz, but really anybody's welcome to just raise their hand and answer the question. It's just meant to kind of remind some of the key themes from the first part. Okay, so first question, what is the strategy that we're employing to reach low error rates for practical applications? Anybody? Yeah, go ahead.
Scalable quantum error correction.
Okay, can you elaborate?
Yeah, so if you can increase, if the number of qubits increase and your logical error rates go down, then bigger is better.
Yeah, that's the right answer. So we're choosing to work with surface codes, and what we've shown here is that we can make several different sizes of surface codes, and if the component error rates stay the same, or mostly the same, which they did, then bigger is better, and we get lower logical error rate, and that's because we're operating a regime where lambda was about 2.14. All right, thank you. All right, so why did we use repetition codes to explore rare error events?
Yeah. They have much lower errors, so we can go towards a regime that we can't reach right now and see what problems we can have in the future.
That's right. Yeah, so surface code error rates are about 10 to the minus 3, and the best ones are about 10 to the minus 3, which if you look on this plot is way up here near the top. And with repetition codes, we can probe very rare error events. Yep. Thank you. Okay, so why was leakage removal important to this experiment? Yeah, go ahead.
I mean, because it caused correlated errors and messed a lot of stuff up.
Yep, that's right. So leakage can persist, and it can spread through the QEC circuit, causing multiple errors. So here, a single leakage event can interact with different parts of the circuit, causing a pattern of errors that are all related to the leakage event happening. And we can quantify the effect, at least at distance 5, where we showed that lambda improved by about 35% by adding what we call DQLR, data qubit leakage removal. All right, thank you. So in part 2, what I wanted to do was choose some topics in QEC that are related to these experiments, but either go deeper or go into slightly different directions. So to just remind you of the outline, so I'll talk about controlling leakage errors. I'll talk a little bit about decoding algorithms and real-time decoding, and then if we have time, I'll talk about color code experiments. Okay, so in general, if some of your qubits stop working for a long time, meaning they just get into a bad state and stay in a bad state, then QEC won't save you. And that's because a qubit that is persistently not functioning is kind of a correlated error. It's over and over again having an error in a burst fashion. And so there's actually a way of visualizing this where we can have qubits that enter a bad state. And what's shown here in these sort of heat map plots is that a qubit that gets into a leaked excited state can actually cause a whole region of errors to happen. So this is leakage in a very uncontrolled fashion. So we don't want that. So let's go back and remind ourselves what leakage is. This is that potential well that transmon qubits live in, or qubit states live in. And at the lowest level, we have the 0 state, and then we number them going up, the 1, 2, 3, 4 states. We choose to use the 0 and 1 states as our qubit. And that means that these states are non-qubit states, and we call them leakage because we say that ideally the system never enters those states, and when it does, it has leaked, it has left the qubit state. Okay, so let's talk about sources of leakage. I think there was a question about this in the first part. Well, leakage can come from a lot of places and arguably almost anything in the circuit. So single qubit gates can have leakage. That's because they are microwave gates, and even though they are quite good, they are not perfect, and that microwave energy can cause leakage. The 2 qubit gates can cause leakage, and that is because, particularly, we've chosen this CZ gate that involves the 2-state explicitly. There's this, remember this swapping operation with the 2-state? And so because it's actually entering the 2-state deliberately and then coming back, sometimes it doesn't come back all the way. There can be an over-rotation error in the gate where it doesn't do a full swap correctly. It does some fraction of a full swap, leaving behind some probability of being in a 2-state. So we can have leakage caused by measurement. Similar to the single qubit gates, it's because we're sending microwave energy into the qubit, and that can excite the qubit into a leak state. And then additionally, idling can incur leakage. And I would say we don't actually fully understand that one. It's something we call heating. It's a qubit is getting excited through some not fully understood mechanism. So leakage can happen in a lot of different ways. So what are some prior approaches to handle leakage? Well, you could do nothing. We found that this doesn't work. You can perform a reset on the measure qubits. Now, there are many different types of reset, and the one we're describing here called MLR means multi-level reset. It will actually reset transmons even if they're in some of these excited states. Even if they're in a 2-state or a 3-state, it will bring them down to the ground state, at least with a pretty high probability. And that actually is helpful. I'll talk about how that on its own is helpful. Did I go? No. Okay. So why is leakage bad for QEC? Wait, did I miss something? I feel like a slide transition got cut off. Sorry. All right, so why is leakage bad for QEC? Well, here's an experiment where we deliberately inject leakage into a surface code. So this is a small surface code. It's maybe not easy to see, but it's a distance 3. The diamonds are data qubits. The circles are measure qubits. And right in the middle, we inject a leak state. And I said that leakage can hop around, and so this is showing it hopping around. So after one QEC cycle, you can almost see there's actually a preference. It sort of goes up in this direction, but it does start to diffuse. So after 1 cycle, 2 cycles, 3 cycles, leakage now could have moved around to different parts of the chip. And so, now this is just getting to be annoying. Like, not only is leakage lasting for a while, but it's moving, it's changing its location. So if we add a multi-level reset, what we're doing is, if leakage ends up on one of the circles, remember the circles are the measure qubits, and we're doing reset to those guys, then this MLR is going to remove it. Turns out that's pretty helpful. As you'll see, where these circles filled in as like red or orange, having leakage population, that is now almost completely removed. And that's because half the qubits in the code, the measure qubits, are having the leakage taken out of them. But it's not everything. Some of the time, leakage just stayed in place, so we're not doing anything about that yet. And sometimes it's able to hop 2 places, right? See, even after 1 cycle, it has a chance of hopping 2 sites and getting onto a different data qubit. So we haven't completely solved leakage, but you can see that we've done something, right? We've made things better, and I'll quantify that in a little bit. Yeah, so leakage can jump from data qubit to data qubit. Okay, that's right. I talked about MLR and the strategy there. This is the other part. So DQLR, data qubit leakage removal. So here what we're doing is we're resetting measure qubits and we're removing data qubit leakage. So we're adding operations to the circuit. This doesn't come for free. We have to do extra gates. But we're now applying a very good filter. It is hard for leakage to get through now because we're doing removal of leakage on the measure qubits and on the data qubits. Now, neither of these operations is perfect, so leakage can sneak through, but we're doing a really good job now, and I'll show you how much better. I talked about this in the first part, that this leakage removal gate is a swapping type interaction. Okay, so what's another way of measuring leakage? Well, or observing leakage removal. So on this plot, which is, there's a linear, it's a funny plot, linear scaled up here for things that are high in probability, and then log scaled down here for things that are in low probability. You can see there's one of those dashed lines on the axis. Okay, so how much leakage is in the system as we're running QEC? So what we do is we run QEC for some number of rounds, and then we measure every qubit using a readout scheme that can tell us if you're leaked. So we have actually leakage measurement here, direct leakage measurement. And so it may be a little hard to see, but there are squares for data qubits and circles for measured qubits. So there's actually 2 lines. It's the same experiment, though. We're just showing measure and data qubit leakage populations separately, which is useful because we'll see the benefits of these different operations. So my colleague who made this slide said this is horrible. And indeed it is. You would not be able to get error correction to work very well if you did that. So then let's add some multi-level reset. Well, the data qubits got better, and that's because the measure qubits are now providing a sink, if you will, a place where leakage can go and get removed. But it's still not good, right? This is still up in the, fraction of qubits that are leaked is more than 1%. Not good. Now the measure qubits, remember those are the circle guys, they got a lot better. They went from a little, 2-3% leakage down to a few times 10 to the minus 4. So they're doing great. That's multi-level reset helping you. Helps a lot with the measure qubits, and there's a side effect where it also helps the data qubits some. And I should maybe say, this is trying to run QEC. We're not injecting leakage. This is leakage happening when it's just present in the QEC cycle. The previous experiments, we injected it for demonstration, but this is not injection. This is leakage that happens despite our best efforts. Yes, there's a question.
With the ancilla qubits, why is there still leakage if you reset all the ancilla qubits?
The gate isn't perfect, is the short answer.
The reset gate.
Yeah, the reset gate isn't perfect. Yeah, in fact.
So maybe you already talked about it, but why is there a difference in leakage for data and measured qubits?
Well, in the red traces, it actually comes down to the specifics of the gates that we're doing and how they're calibrated. So this really depends on the experiment itself. Remember that we implement our 2-qubit gates by frequency tuning our qubits. And so before we implement a gate, we make a choice of the sort of base or idle frequency of a qubit. And it's going to be different for different qubits. And often there's a staggered pattern where measure qubits are high and data qubits are low or something, or maybe it's the other way. Anyway, the point is there is these patterns where there's an asymmetry that is consistent where one of these qubits is higher frequency than the other. And the way the CZ gate generates leakage also follows that asymmetry. And so in this case, it is preferentially putting leakage on the data qubit. And then in the green traces, why are they so far apart? And that's because we're doing leakage removal on the measured qubits. Yeah. Yes?
I also want to ask, is the leakage itself is random and spontaneous? So which means we can't really predict it.
That's right.
And also you mentioned that to adopt the multi-layer reset, we need actual resources, actual gates in the circuit. So we you first detected there's a leakage and then apply those actual gates to the circuit, or you just put them as a intrinsic property to the circuit, to the logical qubits.
So to answer your question, I'll sort of use these diagrams. Yeah, okay, I'll try to summarize. Let me know if I didn't say it right. You were asking that if we don't know if leakage is into the circuit, do we have to react by inserting these extra gates to take it out? Yes. Yeah, so there is no feedback in the circuit, meaning we do all of these gates unconditionally, and we also don't know when we're doing the QEC circuit, whether leakage has happened or not. So these leakage removal operations are preventative. In fact, most of the time we put them in all the time, and most of the time leakage isn't there. But it means that they will work without knowledge of whether leakage has happened. They're not free. They are sources of error in and of themselves. So there's a trade-off there. You're doing something all the time that's not needed all the time. The alternative, though, seems very, very challenging. To somehow detect leakage and change the gates you're going to do in real time is technically very difficult for, say, control electronics. So in this case, the MLR is a special reset gate. It's done all the time. And then DQLR, there's MLR before it, and then DQLR is some extra gates that we insert to every data measure qubit pair in every cycle. So it's always present. And it's sort of acting as this sort of like automatic filter of leakage.
How many, sorry, just a follow-up question. How many resources do you need to like do those gates to carry in the circuit?
Well, it's using elements that we already have, meaning that, we need a reset, and MLR is a particularly attractive form of reset. And then the DQLR, this interaction is a close cousin of the CZ gate. It's a slightly different frequency tuning, but it's using the same control knobs, just with different parameters. And then there's another reset that comes after it. So what it does is it makes the QEC cycle longer, and you have some extra gates that can themselves add error. But there's a net win, which is that leakage is so damaging to QEC that it's worth paying a little bit of extra cost in time and complexity to remove it. Yeah, go ahead.
Is leakage a non-Markovian process, and can QEC only save us from Markovian?
Okay, two questions there. So leakage is probably Markovian most of the time for our system. I'm trying to choose my words carefully because remember there's all these different sources, so I'm doing an inventory. But from CZ gate to CZ gate, it's going to be independent. Each CZ gate, one CZ gate causing leakage doesn't cause the next one to have leakage. Now, important thing to remember about leakage is I'm talking about leakage itself, like the probability of leakage happening. Because once you have leakage, it causes non-Markovian errors because it is this persistent error. So just being distinct, the probability of generating leakage, I think, is Markovian process most of the time. The reason why I'm doing some thinking while I'm answering the question is there are some exotic mechanisms like crosstalk that can cause correlated errors, possibly in time. So I don't want to say it's always Markovian, but I think if you're just looking at the weighted sum of contributions to leakage, I think most of them are Markovian for our system. And then you asked about can QEC fix non-Markovian errors, and the answer is it can fix non-Markovian errors in most cases. So the fact that an error is non-Markovian is not on its own a killer. And the reason is the stabilizer measurements take these non-Markovian errors and project them down into random poly errors. But there are subtleties to that statement. So for example, if you have a single qubit, a single data qubit, say, that has a burst of errors, there are ways in which this can fool a decoder. And so then it becomes a question of, is your decoder well informed about such events? And this becomes a very kind of involved discussion. But non-Markovian errors are not intrinsically unfixable. They can add complexity, though.
So the reason QEC can't help us against these problems is because it's a correlated leakage, because it's correlated error, not because of its.
So the
Trying to see what makes it.
so the issue is that leakage can cause a burst of errors close to each other. And that's what I'm saying is correlated, is in that like either in space or in time, there's some region where a lot of errors happen simultaneously, and they're all attributable to a single leakage event. And that's why you want to contain leakage, because these burst errors significantly weaken the performance of error correction. If they're completely uncontrolled, they can actually, you know, basically set a noise floor themselves. Yes.
I'm wondering, I see in the picture that this ISO gate will transfer the leakage error from the data qubit to the measurement qubit and add a reset gate to remove the leakage. But I am wondering how this ISO gate identify this is a leakage error and this is not another qubit state change caused by its original operation or something like it.
So I didn't show, you know, energy level diagrams or Hamiltonians here that would make this a little bit clearer. But the short answer is this is a swap operation, or it says I swap, but it turns out the I part doesn't, it's a detail, but it doesn't affect the gate itself. It's a swap operation where if the bottom qubit is in the 0 state and the top qubit is in the 2 state, the lowest leakage state, then what it does is it swaps a single excitation over here. And that takes you from 2, 0 to 1, 1. Now a 1 state up top is no longer leaked. It's now back into a qubit state. And a 1 state down here is just undesirable, and we want to reset it. So it is a gate in that the operation is essentially transparent if this qubit is not leaked, and if it's in the 2 state, it will bring it back to a qubit state. But there's no information to the outside world that leakage had occurred. There's no readout here. I hope that answered your question. Yeah.
For the mean data plots you showed for the lambda equals to 2 data plots, like
Yeah.
which ones of these schemes were you using?
We were using the rightmost. So MLR, the multi-level reset, and DQLR, the data qubit leakage removal. We were using both.
Oh, okay. And this fits within the 1 microsecond cycle time in that experiment.
That's right.
Okay.
Yeah, and the main reason that it fits is there's no readout. Readout's the slowest thing. Or we didn't add any more readout. There's only 1 readout per cycle.
I see.
Okay, I'm gonna go here.
I think there is a paper published by Google called the time dynamic surface code, which can by time dynamics, the surface code can exchange their data qubit and the measurement qubit. So the MLR can reset the both of the qubit because they are changing by QEC cycles. How do you think of the time dynamic technology compared to the DQLR?
You're right. There are flavors of surface codes, variations on the circuit itself that can imbue different properties. And one of them allows you to have the data qubits alternating sites. So the labeled data qubit moves to different physical locations. And as you said, you can then do, if leakage doesn't move, so like the data moves but the leakage doesn't, then if you're doing MLR to just half the qubits, then by alternating, you will remove leakage everywhere every other cycle. Half on one cycle, half on the next cycle. And you're right, we had a recent paper that showed that. It got very similar performance. So we got another lambda of 2 or so without the DQLR. It's an alternative that we're exploring.
Thank you.
Yeah, in the back.
This 2-qubit gate there, is that, what mathematical properties, what kind of animal is it? It's not unitary, right?
This is unitary.
It is unitary.
This is a swapping interaction between 2, 0 and 1, 1.
That's all it is.
Yeah.
But then it has this additional effect that outside of the 2 levels, it can bring down.
Yeah, that's right, because it's a resonant effect. We're bringing 2, 0 and 1, 1 into resonance, and the anharmonicity of the system means that none of the other qubit states are in resonance.
is that something that would be useful for if we had 2 threads and we wanted to actually use the second level that's in there? Is that okay?
Yeah, probably. Yeah. I mean, all of these gates are, there's like 2 flavors of gates in our system. There are the gates that drive transitions between energy levels. So like our microwave gates could take you from 0 to 1. They can also take you from 1 to 2 if you drive a different frequency and so forth. And then there are gates that are excitation preserving. And these are swapping interactions between 2 qubits where you conserve the number of photons in the system. And so between those 2, you can play all sorts of games with these higher excited states. Yes?
So is there a way to like, I guess like build this into your error correction cycle? Like maybe like, you know, add this to like a stabilizer formula or something?
Well, what we're doing right now is the naive thing, which is we just stick it on at the end. You're asking, can we somehow fold it in? I don't know, maybe. I haven't thought about it. It's definitely worth trying, or worth thinking about.
You said already do the, this is a precaution against leakage, but you said that most of the time you probably just do it and it's actually not useful. Have you checked how many times when you apply it it's actually completely useless, and then how many times it actually?
Well, I wouldn't call it useless because
it's
automatic.
No apply it,
Yeah.
right?
That's kind of what this plot is showing, right? Like, so, leakage is building up if you do nothing. And then with MLR, the leakage on the measure qubits is very, very suppressed. And for data qubits, it's still building up, but it reaches some lower saturation value. So that means that there's this balance between the rate at which leakage is being generated and the rate at which it finds its way to a measure qubit to be removed. So those 2 rates saturate into this 1.5% leakage population. And then the final part I hadn't shown before is the blue is now turning on data qubit leakage removal. And so it's, remember there's a cutout here in the scale. So the data qubits went from 1.5% leakage population to about 10 to the minus 3. This is actually more than a factor of 10 suppression. And measure qubits actually got even a little bit better, presumably because these guys were not, polluting them with leakage. And yeah, so now leakage is being removed quite well from the system. Populations went from a few percent to 10 to the minus 3 or lower. All right. Oh, and let's return to this plot before. This was the experiment where we intentionally inject leakage. And so now you can see that after a few cycles, you don't see it anymore. There is actually an interesting effect. You can see the efficiency of data qubit leakage removal here, because there's still some signal left after 1 round of data qubit leakage removal. But remember, this is a log-scaled color scheme, so this corresponds to, I don't know how much it is, a factor of, more than 10, maybe 100 suppression and leakage after 1 round. Yes?
Sorry, I just have a question about like how bad the leakage is in terms of like are you just leaking from like into Cat2, or are you also like leaking so far up that like you're not even in a bound state of the trend?
Good question. This is 2-state. That was by design. This is 2-state because that's what we're looking for. But you can get higher states. They're more problematic. All I can say is that seems to happen even more rarely, which is good. But I think it's something to keep an eye on, is what I would say.
Why are the data qubits affected more from the leakage as compared to measure?
I believe it is because of this frequency asymmetry that because of various properties of how we're calibrating our devices, we end up with this bias where the data qubits are like at either a higher or lower frequency than the measure qubits systematically. And then the CZ gate preferentially puts leakage on one or the other. I don't remember the details if it's high or low, but it goes to one side, and I think we always put that side on the data qubits for other reasons, for reasons about calibration.
So that heat map, that what's the value there on the bar?
So this is a leakage population, and it's a log-scaled axis. So like the top is unity or 100%, and then this is 10%, 1%, 0.1% leakage population.
But in your example there, you have a dark square, right? That's either has leakage or no leakage. How can you get a gray one? Yeah.
So in this case, this is an experiment where we initialize a surface code, but then we use a microwave gate to intentionally put leakage on this one side. And so that's why it's dark red.
Right. But give me the sense that you have some intensity encoded here. Is it? Because you look at the second graph, that it's slightly lighter, right?
That's right.
It's not a 0 and 1.
So what happens is we've run one cycle of surface code error correction and the MLR plus DQLR, all of the leakage removal. And so this is how much our injected leakage population has been suppressed in the color scheme. So it went from something up here to like something down here. Well, we're measuring leakage everywhere, because remember we did these other experiments with less leakage removal in the system to show all the problems that happen if you don't remove leakage. But this is where we're throwing everything at it, right? We're doing all the leakage removal that we can, measure qubits and data qubits. And we're showing that leakage isn't moving around like it did up there. And also it's decaying quite quickly, which did not happen here.
Yeah, did you say that so after the first cycle, you run the QEC and the DQLR at the same time? Is that what you said, or did I?
Yeah, that's right. We run the stabilizer measurement circuit, and then at the end of that circuit, we then do leakage removal. It's appended, yes, to the end of the circuit. And then we do another stabilizer circuit and more leakage removal and so forth. Okay. So I actually kind of showed this data earlier, but before I transition, when we run the surface code experiment without DQLR, we get a lambda of about 1.6. And then when we add DQLR, we get a lambda of about 2.14. So that's a 35% increase in lambda in experimental data. Which, by the way, we also predicted similar effects from simulations. Okay, so another interesting topic in applied quantum error correction is decoding algorithms. Oh, there's a question.
Yeah, about the plot in the previous slide, I was wondering if you had done this for the 7, d equals to 7 case.
That's a good question. I'm actually not sure if we have that data, because we were pretty convinced by this, and so I'm not sure, actually.
So, I mean, it's the approach to resolving this seems somewhat straightforward, so I'm curious as to why, is it just because the error scale was completely different, that you had, like, this kind of thought process was not attempted before, or?
Well, first, many things do seem obvious in hindsight that aren't obvious ahead of time. Leakage has been identified as a problem for QEC for 20 years, or maybe more. So in the general or abstract sense, that was known. But quantifying it, it depends on the system that you have. So the leakage in Google's latest superconducting processor is going to be different than our previous generation. It's going to be different than some other teams' superconducting processor. And then, of course, qubits that aren't superconducting have their own dynamics as well. So in some ways, you have so many problems to solve in building a quantum error correction device that you prioritize, you tackle them in the order that seems the most important. And we didn't see this mattering very much in past devices where the error rates were higher. So for us, we crossed over into a regime where this was starting to be a big limiter, and that's when we implemented it. But there's papers, even from the Google team, or at least researchers at the Google team, maybe papers from previous academic work, saying you got to think about leakage going back 10 years. So this was not a surprise to us. It wouldn't be a surprise to many people in the field that leakage is a problem. It's just when does it become enough of a problem that you invest the resources in addressing it? Yeah, question.
So leakage is different than erasure error, right?
Oh, that's a good question. They are related, but they are neither the same nor completely different. Erasure errors are errors where you have some information that the error has happened. That's what makes it an erasure error, is that you know that it happened. Leakage errors is a qubit leaves the qubit subspace. It becomes some excited state. So the reason they're different in that way, leakage can happen without any heralding. Erasure always has heralding, a signal coming out. But they're not necessarily completely different because erasure errors can be leakage, right? Sometimes you can have leakage that is heralded. So they're interesting concepts, but they're partially overlapping, but not the same, not completely different. Yes?
So it seems like your leakage population kind of saturates, at least for your measured qubits, at like 10 to the minus 4.
Yeah, it's maybe a little lower than that, but yeah.
So is it that your reset operation just can't prepare a state with less than that overlap with the 2 state, or is there a different reason why it's
It's a good question. I think that it's a combination of effects. So one way of thinking about these leakage removal processes is in terms of efficiency. So if leakage is present, what is the probability that it gets removed? If the efficiency is 99% and leakage probability of being generated is 1%, then you get 2 factors of 100, right? 1% times 1%, and you get something like 10 to the minus 4. But you saw there was multiple inputs to that equation, right? Like the probability of leakage happening and the efficiency at which it's removed. So if the device was configured differently and leakage generation rate went up, then this number would go up too.
So it has nothing to do with the actual reset operation, like with that not being like perfect?
Well, in the sense that efficiency is a measure of imperfection, right? Because like the ideal multi-level reset is 100% efficient. Yeah, and so inefficiency is part of it, and the rate at which leakage happens is another part of it. Yeah.
I have a question. So DQLR basically uses what they call it the leakage ISWAP, right? So basically targets the states that are like leaked, and then they transform it back into they reset it into the measured qubits. Is it like that?
Yeah, that is right. So I'll go back to this cartoon. So we call this a leakage ISWAP. That's because it's not a qubit ISWAP. A qubit ISWAP would be only between qubit states. This is actually a swapping interaction that involves a leak state. And what it does is, if this upper qubit is actually in the 2 state, is leaked, then it will pull an excitation, one photon, if you will, although some people don't like me using that term, pull an excitation down here. And so then what's left behind is this is in the 1 state, and then down here is in the 1 state. And so leakage is no longer there because it's almost like it got pulled into 2 places.
Erase it, but how do you detect that actually that was leaked? Like, wouldn't it happen that also like instead of corrected, it could be making it worse?
It can make it worse, yeah. Well, I didn't say much about this, so now let's talk a little bit about the problems. This is a gate. It has to be calibrated. It's never going to be calibrated perfectly. And so in and of itself, it can cause problems. It's a gate that interacts with leakage. so it can cause leakage. And even if that gate is perfect, another problem is actually this reset right here. So remember that I said this is a swapping interaction between 2, 0, and 1, 1. So what I mean by that is 2 up top, 0 at bottom. And then if everything goes perfectly, you're left with 1 up top, 1 at bottom. And if you had a 1 state or a 0 state here, a non-leak state, it should just pass through unchanged. However, all of that assumes that the bottom qubit starts in 0. And we make that assumption because we say, oh, we just did a reset. But resets are not perfect. And so one thing that can happen is this qubit is not leaked. It is in the 1 state. This reset does the wrong thing sometimes. And it puts this in a 1 state. It will actually cause leakage. It's putting leakage into the system that wasn't there before. This is a rare event, but it matters.
And is there a way to overcome it? I don't know, like you do it again?
I mean, you just try to make these gates better. You try to make your reset better. But at some point, it is some non-zero error rate process.
Here you're assuming that the reset is the one that is good enough.
Yes, in this case, the reset gate is pretty good.
Okay.
And so there is a net win where the amount that this operation, composite operation, generates leakage is significantly less than the amount of leakage it removes. But that is a balance of parameters, and you can't say that that's always favorable. There could be ways of configuring a device where DQLR is harmful. Yeah.
Sorry, just a quick question. So I was wondering whether you tried, or what was your procedure about applying the DQLR, like after every 2 qubit gate or after every single qubit gate, or while it's idling, and what are the differences when you do these different approaches and how they reduce leakage?
So I'm going to go back pretty far because the diagram I want is actually from the first part. Sorry for that. So this is the full QEC cycle that we're doing. And so everything except the purple part is normal QEC stuff, right? This is stuff that runs the surface code. And then we add leakage removal onto it. And we do it at the very end of the cycle. So it's only once per cycle, not per gate, per physical gate. And in particular, it fits into this spot because we need this lower qubit to be in the 0 state. And we know at one point in the circuit that it's in the 0 state, and that's right here because it's right after a reset. So there's actually sort of a interplay or coupling between the MLR and the DQLR, that this blue reset, the MLR, gives us a pretty strong confidence that we're in the 0 state, which makes us feel safe about doing the DQLR, because as in the previous question, if that reset wasn't doing a good job, then the DQLR will actually do a bad job.
But by that point, haven't you already risked leakage, traveling through the CNOT gates? If leakages happen, say after the Hadamard gate over there, haven't you risked leakage mobility through the next couple of CNOT gates or whatever?
So the thing is, we do this everywhere, so that there really isn't any way for leakage to evade it, right? We do this reset, which is an MLR, the multi-level reset, we do it to all the measured qubits. And then after that, we do DQLR, which is a composite operation, but it's touching all the data qubits. And so there isn't anywhere for leakage. There's no way for leakage to evade this. Yes?
I'm a little confused. You said when data and measure is 1, 0, it should just pass through without affecting the other. But you also said when it's 0, 1, then the measurement qubit may inject some leakage error into it. So does 1, 0 change or not?
So what happens is, if this bottom qubit is in 0 and the top qubit is not leaked, it should pass through unchanged. If this bottom qubit is in 0 and the top qubit is 2, the most likely leak state, then that leakage is removed, or it's sort of downgraded to this now is a 1 state. That's everything working as intended. if this bottom qubit is a 1 because the reset failed, and the top qubit is not leaked, but it's in the 1 state, yeah, then you will actually get promoted leakage. It will put leakage into the system. So everything works as intended if this reset works. And if the reset, yeah, go ahead.
So 1 0 goes to 1 0 and 1 1 goes to something else, not 1 1?
2 0.
2 oh, okay.
Yeah, it creates a 2 state at the top.
Thank you.
Yeah, there's a symmetry in this gate where it will take 2 0 to 1 1, and it will take 1 1 to 2 0. It's swapping those 2 states. Yes?
Does the saturation leakage population always saturate to some value, even if there's no reset done? And also, what determines the value of that saturation?
It's a competition of rates. There's going to be up and down transitions. Up meaning like a qubit goes up to a leak state because they're excited, and down meaning there's some process by which a leak state decays. Reset is an active decay process, but there's also energy relaxation, T1 processes. And so, you know, to a first order approximation, it is just like, you know, a two rate process. Like you have an up rate and a down rate, and like the ratio of them is like roughly the saturation value. Okay, so I had gone pretty far back. Now I'm going to bring us forward again. Okay, sorry about that. Okay, this is where we were. So this is actually the conclusion, just saying that when we put up this net, if you will, that catches all the leakage, we are able to show that leakage is being removed pretty effectively from the system and suppressed to quite low levels while we're running error correction. All right, the next topic. We have time. We have some time. Decoding algorithms and real-time decoding. So this is drawn from a figure I showed earlier in the talk. This is, again, a 3D diagram sort of showing time flowing left to right, and how if, for example, you have an error, like a red Z error, when it goes into the syndrome measurement circuit, it turns into flipped parity checks. These stabilizers get flipped. And in particular, there are like known patterns where like a Z error at the start of the syndrome, the QEC cycle, will turn into these two parity checks flipping. And we can easily use a computer to generate all these patterns for any single error, what measurements do we observe. And we can use that to configure a decoder. There's another example here where if there's an error on a measure qubit, it flips parity checks and so forth. But here's actually kind of the important part. The surface code itself has a property that if we look at the parity checks individually, the X and the Z, each single error produces 1 or 2 flip stabilizers. It has to produce more than 0. If it produced 0, then we wouldn't detect it, and that's bad. So it's producing more than 0, but for general QEC codes, there's no bound on how many stabilizers might be flipped. And in fact, for general decoding of classical codes, this can be a very hard problem. But surface codes have structure to them. They have special properties, and one of those is that every single error in the circuit will flip 1 or 2 stabilizers. Most of the time 2. It can be 1 at the edges of the code, but in the interior, for most of the code, it's flipping 2 stabilizers at a time. This is actually a really useful property. It turns out that what you can then do is you can make a graph, and that graph is your parity flip detections. We call them detectors. And every error can be an edge. And that's because it either is flipping 2 of them, so that's an edge, and its endpoints are the 2 nodes that get flipped, Or sometimes it's flipping one of them. And like I said, this happens kind of at the boundaries of the code. Okay, but it's always a graph. You can say I'm changing notation a little bit to say an edge has one node, but whatever, just call it a half edge if you want to. It's a graph, and every error, it says, activates one or two detectors, and that's a property of the surface code. It's a really nice property. And this allows us to run a decoding algorithm called minimum weight perfect matching. And the way minimum weight perfect matching works is you say that I have these nodes that have been excited, and I have to match them up in pairs. And you can show that by construction, that is true of the surface code, right? If I had, let's say I had this configuration, and let's say I only have these edges right here, well, I would say say in a ring, well, these two nodes are not directly adjacent to each other. But how might I explain this? I'd say well, there was an edge here, and there was an edge here. So those two edges touching in the same node means that it flipped twice. So you either have edges or you have paths because two edges meet each other. So always you're matching up pairs. That's just something cool and kind of unique to surface codes. And you might say, all right, fine. Why does that matter? The reason why it matters is there is a well-studied algorithm called minimum weight perfect matching that says that for an arbitrary graph, if you need to match up pairs of nodes, this can be done in polynomial time. It's like a guarantee. It always works. And that's really cool. That means that we always have an efficient decoder for surface codes. And you might even argue this is one of the reasons why surface codes have been so popular is because decoding was solved problem from the beginning. Solved problem is overselling it. Lots of work has been done to make decoders even more accurate, but there was a good decoder from almost the very beginning. And that really helped people get excited about surface codes. So I don't want to show this for too long because it's mesmerizing, but the point is this is like real data where we're running a decoder and we're matching up pairs of things. This is what decoders do. Each time it blinks, that's a different shot, and it's just showing how decoders match things up. If you're curious, it's separating the X and Z checks. So where it says red, that means it's X checks being matched up, and blue, it's Z checks being matched up. This is what decoders do. They have data come in, and they match things up. And even for shots like this, they can do it really fast, in microseconds. So I'll talk about speed in just a moment, but there's this other thing, this other really interesting decoder, neural network decoder. So the neural network decoder is taking some deep insights from transformers, which, as you may know, have been central to the last few years of AI development, and applying them to decoding surface codes. And it turns out that transformers seem to be able to learn really complex correlated models, in this case, correlated error models, and using some insights, in this case, a recurrent neural network running on top, insights from the structure of the problem, that is that there's a recurrent nature because we're running a periodic cycle of gates. On top of the transformer was able to learn really well what was happening in the device. And so this is data from the 2023 experiment where we didn't have the neural network decoder when we did that experiment, but we analyzed it after the fact. The data's online if you want to go find it. Run your own decoder. And the point is that anything that starts with an M over here, these are matching decoders, variants of matching decoding. And the neural network decoders, through various forms of fine-tuning, were able to get even better performance. So there was kind of a little hair of an advantage here. Well, sorry, I don't have the other slide here. But this was run in the most recent experiment where they also got a higher lambda, about 5% higher lambda in the recent experiment. Yeah.
I'm sorry, previously you said that for Y errors, you kind of want to treat both the X and Z stabilizers together to get better performance. But in that case, you would flip more than two stabilizers, I suppose. So
that's
how
right.
does matching apply there?
Yeah, that's a really good question. What you can do as the base case, the simple thing, is treat them separately. I have X checks, I have Z checks. I think about them completely independently. That was the sort of original implementation of matching for surface codes. And it works. And the reason is Y errors will still only cause at most 2 flips in those separate groups, 2 X flips and or 2 Z flips. There's an insight there, though, that like these are not independent. What I just described to you is independent decoding. Think about them separately, but the 2 sets of measurements have information about each other. That's actually shown here. For technical reasons, this is called pi matching. That's actually the name of an open source repo. But the gray bar is uncorrelated matching, the independent style. And then the darker, or whatever, medium dark gray, is correlated matching. And this is actually using knowledge of the 2 different syndrome sets together. Specifically, if you want to get into the details, it's looking at the detection events and changing the edge weights for the matching problem. The matching graph has dynamically modified weights based on the detection events you see. BP kind of does that to an even more advanced degree using belief propagation. And the neural network decoder just kind of learns correlations and encodes them internally. So yeah, you definitely want to exploit that information.
So, yeah, for the regional data, for the graph, like, are those edges all equally?
They can be, but it's better if they are actually weighted according to the probabilities of errors. Loosely speaking, they are the logarithm of the probability of errors. There's a technical reason for that, which I can explain maybe after the session. But yeah, the properly weighted graphs are more performant than uniform weighted graphs. They give you lower logical error rate.
You had a slide before with different lambda values for, it's way back in the first session, you don't have to go back.
Oh, okay.
For various matching algorithms, how do those matching algorithms match up to those that you showed on the plot? So like, which one is the real-time one? Which one is synthetic matching?
Oh, I'll get to that. Yeah, so this is the neural network decoder. This is showing its performance on the older experiment. This is when lambda was about 1, which you can kind of visually see, like distance 3 and distance 5 are about the same. Before moving on, I'll just say that the runtime performance was quantified, you can see here that this is decoding time per cycle versus code distance, they ran it up to even very large code distances just to see how it was running, and it's something in the tens of microseconds time per cycle, where the cycle time itself is like 1 microsecond. So that's why I was saying that like it's approaching the performance you would want for real time, but there's more engineering work to do. For comparison, matching is shown here, and matching is faster. Matching has another appealing property, which is that the algorithm gets faster when the error rates get lower, and that's because matching only does as much work as it needs to. It's matching pairs of things, pairs of these flip stabilizers. If you have fewer flip stabilizers, it has less work to do. For better or worse, the neural network decoder has a constant runtime for any error rate, or error per cycle, I mean. Yeah.
Could you say again, what is it running on? Is it running on your laptop or is it running on an accelerator? Or what is it running on?
It is running on an accelerator.
Uh-huh.
But not my laptop. Okay, so there was also a question about comparing the different decoding algorithms for the recent experiments. So this is now a lambda of 2, or greater than 2. Over here we have, this is the matching without correlations, which is here just called minimum weight perfect matching. The real-time algorithm is using correlations, where I was talking about dynamically changing graph weights. Synthetic matching does that, but it does some other stuff too to be even more accurate. And then the neural network, which is the most accurate, is trained to high performance using data from the device and state-of-the-art techniques for neural network training. There was a question. Did I cover that question for the synthetic matching in real time?
Which was synthetic matching corresponding to belief matching, or was it the?
This is a newer algorithm. So the matching with belief propagation, which is just called belief match, is another algorithm. I think we might have even included data for it in the paper, maybe in the supplement. Synthetic matching is a little bit better. So, and then there's real-time decoding. So real-time decoding, well, maybe before I go on, you'll see that it's actually competitive. Like, it's not quite as good as the best offline decoders. These two are offline. This also is offline, by the way. But these two are offline. They do extra work, and they don't quite run in real time. But you're not far from that performance with what we can run in real time. So that's interesting. So how are we doing that? So matching runs on this graph, like I said, and we're actually building this graph as we go through the experiment. So there is a special computer. It has like a 64-core CPU on it. Has special software, all the bells and whistles. And what it's doing is taking measurements from the experiment in real time and building this graph as it needs it and basically stitching it together. It does it in these chunks or windows. It glues pieces of graph together as they're needed. And so we wanted to confirm that this was running in real time. Well, real time at a minimum means that you're keeping up with the data as it's coming in. And so the way we observe that is we say, well, what was the latency for the experiment? So we sweep the number of cycles, and in fact, we're running experiments up to 1 million cycles. These are long QEC experiments. And we have all these measurements coming in, and we say, what was the latency from the end of the experiment to the decoder saying, I know the answer. I can tell you where all the errors happened. And if you're not keeping up with data, this will not be bounded, right? It means that longer experiments, you're building up a backlog, and the decoder is not able to keep up. So we're actually showing that the decoder is indeed keeping up with data. The latency was a little bit less than 100 microseconds, independent of how long the experiment was, like whether it was 1,000 cycles or 1 million cycles. So it really is keeping up, and it definitely is decoding, especially for these longer experiments, it's decoding live. Like, the experiment is still running, and the decoder is processing the measurements it received, like 100 microseconds before that. So it's evolving its state with the experiment. So that was pretty cool. This plot is also just showing that we did some simulations with realistic noise models, and we got pretty similar performance. So the decoder is behaving in a predictable way when we attach it to the experiment. I can maybe explain a little bit. So shot latency means the latency at the shot level. So the shot is do a full experiment and then see how long the decoder takes to finish. The sub-shot latency is kind of a technical term. It means that we're collecting all these timestamps while this system is running, because we have all these diagnostics built into the system. And so we're collecting timestamps at intermediate states, and we say compared to where the experiment is, what's the timestamp for the decoder? And it's just showing that even inside the shot, it's continuously tracking. It's always about 100 or a little less than 100 microseconds behind.
Does that mean that every non-Clifford gate need to wait for that 100 microseconds?
Yeah, there are a variety of ways of implementing non-Clifford gates, so I don't want to give a sweeping answer everywhere, but in most cases the answer is yes. The answer is that if we had a non-Clifford gate that was dependent on the output of a decoder, that the delay with the current system would be whatever it is, 60 or 70 microseconds. So this is definitely something we want to improve, because we want that to be lower. But the short answer to your question is yes. If we were trying to use this in a circuit with non-Clifford gates, this is the delay that would be incurred, the latency, yeah.
Also, if you keep postponing the error correction through the Clifford gate, is it going to complicate your deploy schemes when you get to the T gate?
Well, that the answer is probably not. So the way you phrased your question maybe intentionally touches on a somewhat complicated topic, which is how do you do decoding for logical gates? I've only shown you decoding for memory. So but you said Clifford gates, which could include logical gates. It depends on how you're handling that, because this procedure does not naively translate into that regime. So there might be ways in which the way we're setting up this like growing graph does not adapt well to logical gates. That's maybe why I paused to answer your question carefully. Yes?
Have you guys tried at all to do like logical entangling gates between two surface code qubits?
I'm going to show you two color code qubits. It's on the docket. Yeah, of course we want to do it. Okay. So specifically, what we do is we have these blocks of graphs. So these are like pieces of this graph. And we have a mini core CPU. And so once we have all the information from one of these blocks, like this right here, we send it to one of a single thread within our CPU to solve that problem. That will take some time. Actually, it's about 70 microseconds. And so we can't just wait for the answer. So the next block that we complete, we send it to another CPU and another one. So this is a multi-threaded system that is continuously running actually many decoding instances in parallel for these blocks. And then when the blocks are done, we fuse them together, which actually is running a little bit more decoding. There's some extra work to resolve at the block boundary, but it's not very bad. And so then after we fuse these blocks, we have this completed decoded syndrome history. And as I said, it's evolving in this streaming fashion where at some point history is complete and we do no more work here, and then the windows all slide forward. And as long as the decoder is solving blocks fast enough, it will have resources, extra threads, to take on the next task. And if it wasn't running fast enough, then there would be some backlog and we would have seen latency explode. Questions? This inset here kind of shows the logical error rates. And for the real-time decoding experiment, it's called ensemble matching, but this is actually synthetic matching. And you can see that it's close to the neural network performance, almost the same level of performance there. Yes?
Yes, so here is like, it is no later than 5, but if you split the distance, you actually might have larger graph.
Yeah, that's right. So real-time at one distance doesn't guarantee real-time at any distance. There are two effects that we hope, and I think anyone working in the field hopes, will cancel out. That is that decoding gets harder as you make your codes bigger, but decoding gets easier as your error rates get lower. And to a reasonably good degree, they get better in the same way, the same proportionality, meaning like if you double the size of your system, double the distance, and you cut the error rates in half, they approximately offset. So if we made a bigger device, but we got the error rates lower, we probably would still be in real time with this system. And of course, we want to make it better on top of all that. Yeah. Yeah.
Related, is it possible to split the catch-up process regions independently?
There are definitely ideas for this, proposals in the literature, and a little bit of simulation work in this area. It kind of falls under a topic known as window decoding. It is definitely possible and seems to be, a little complicated.
Can you explain more details about the fuse? Does it just do another blossom on the fused graph, or it use decoding result from the every every block and fuse the decoding result to a larger decoding result.
There are different ways of doing this, which actually touches on the windowed question before. The way we're doing it is when these pieces are solved individually, this first top step, they are actually incomplete solutions, meaning that they run the Blossom algorithm up to the point where it doesn't know what to do next, but it hasn't done anything wrong. It means it's an incomplete solution, but hasn't stepped out of valid solutions. And then when they're fused together, you actually do turn Blossom back on, now that it has information about what the neighboring block has done, and then they complete. It's not the only way to do it, but it is the way we did it here. Okay. Oh, 11 minutes for color codes. I think color codes are fun. Okay, color codes, they are similar to surface codes, but they're not the same. They have some interesting properties. So what is a color code? Well, similar to surface codes, you can describe them with these pictures that look like tiles you might see in your bathroom or something. They're regular polygon patterns. They're not surface codes. They're a little bit different in a couple of ways. The first important thing is that every tile actually represents two stabilizers. So if we have a red tile, for example, it means that this is two stabilizers, not just one stabilizer. Like for the surface code, it would be just one stabilizer for a tile. The reason they're called color codes is they have a coloring property where you never have two tiles of the same color touching each other. There are other mathematical constraints that I won't go through, but that's kind of how they got their name, is this coloring property. They have this version that we've chosen. There's actually a whole family of different color codes. The one we've chosen can be measured with this syndrome circuit, which if you just look at it, you would say, that's more gates. And you're right, it is more gates. And that could be a concern. So it does do something interesting, though. It measures two stabilizers at the same time. We have a circuit in here for measuring the Z stabilizer and the X stabilizer together. That's really cool. And then the other thing that's really nice about this is that if you look at this, you would see like, oh, wait, those qubits are in a square grid. And if you maybe inspect a little bit closer, like where those gray lines are, you say, oh, look, they're only using nearest neighbor gates. And so that means we can run them on our processor. We made a processor for surface codes, or that's what we had in mind, and we can run color codes too. And that's really interesting. So it means that, there's now like essentially two codes that our hardware effort can take seriously, right? And this expands our options. Color codes may have some advantages. They have some disadvantages. But it's also just fun. And they make prettier pictures, in my opinion. So the coloring is actually related to the dimensionality. It's always D+1. So for 2D color codes, those that fit in a plane, there are 3 colors. If you go to 3D color codes, which people do study, maybe even Misha talked about it, because I know they've done some experiments. Misha Lukin talked about it earlier. They did some experiments. You have 4 colors. So it's D+1 for whatever dimensionality you're in. Okay. Yeah, so this is doing a distance 5 color code on one of our 72-qubit processors, what we would normally use for a distance 5 surface code. The summary is that we showed here that there's a lambda value of 1.56 for the color code compared to 2.14 for the color or for the surface code. Here's the data. This is an error budget where we say like what percentages we attribute to various error sources. The other thing, by the way, I should say about this experiment, the lead experimentalist, Nathan Lacroix, actually did this as as an intern, as a student researcher. Now, obviously, he had help because running these experiments is complicated, but it kind of shows, first of all, good for him. Second of all, the versatility of this platform. Oh, you want to try a different code? It's an intern project. A very, very good intern project.
How do you do the decoding on the color code? Because you see here a data arrow on the data qubit now flips 3 stabilizer, which is don't fit the assumption that you use MWPM in surface code.
Yeah, really good question. Decoding is harder for color codes. And in fact, matching doesn't work very well. There are ways of reducing it to a matching problem, and you lose accuracy. I wonder if I have a slide on that. Sorry, let me just see. I'll talk a little bit about it here. But yeah, it is harder. I would say that decoders for color codes are less well developed. Maybe I should say, okay, what am I plotting here if I just said decoding is hard? This is for the neural network decoder.
Okay.
Another thing that, it's interesting that it adapts to other codes.
Can you say again the relationship between the distance and the number of colors?
It's D plus 1. So for a 2D color code, you have 3 colors.
Okay, how do you get D equal to 5 in this case?
Sorry, I'm overusing terminology. So it's dimensionality plus 1. So a 2D, 2-dimension color code has 3 colors for its tiles. This is distance, the distance 5, which is essentially the diameter, if you will. The width of the patch is 5 data qubits.
So I think with 3 colors, you can get the arbitrary number of arbitrary distance?
Yes. Yes, that's right. For this particular family of codes, they're triangles, but you just make bigger triangles instead of squares as you have for surface codes.
The number of qubits that we are using for color code, I believe it's reduced from the planar surface codes. Is it the same or even less than the rotated version of surface code?
That is a good question. I'm going to actually come to this a little bit later. So for the same distance, this code uses fewer physical qubits. It is 75%, 3/4. Okay, another interesting experiment here is that color codes have the property that all Clifford gates are transversal. And in particular, this is really useful for the single qubit Clifford gates because they can just be applied directly. So this is a randomized benchmarking experiment where kind of you can see the sequence up here. We're doing logical random Clifford gates interleaved with the QEC cycles. So the reference, if you will, is running us just QEC, a memory experiment, and then the benchmarking is doing a random Clifford every cycle, which is a single qubit gate, which is very fast. And the summary is that these two curves are very close to each other, and so if you want to do logical single qubit Clifford gates, the error per gate, added error per gate is quite low. And it was significantly lower than the error per QEC cycle. Okay, so we're doing logical gates with color codes, faster than we can do them with surface codes, it turns out. But we also did a 2-qubit experiment. So this is 2 logical qubits being entangled together using a technique known as lattice surgery. The reason why it gets that name is that you start out with 2 independent logical qubits, and then you change the tiles, the stabilizer measurements, in a way that fuses them into one continuous patch, and then you separate it again. So it's the surgery part of the name. So this is a building block for logical CNOT. What it is logical parity measurement. You're measuring the, I forget which it is, but it's symmetric. Either the XX or the ZZ logical parity of 2 logical qubits. And doing it in a fault-tolerant way. This is some logical Bell state analysis and state fidelity. Yeah, and also because these guys are a little bit smaller, we're able to do 2 distance 3 qubits on this device. a 72-qubit device that doesn't have space for 2 distance 3 surface codes. And so on the subject of color codes being a little bit smaller, I said the experiment found a lower lambda. And we can attribute that to the QEC cycle has more gates in it. And the reason it has more gates in it is the stabilizers have higher weight. Most stabilizers touch 6 qubits instead of 4 for the surface code. So you need more gates to measure stabilizers. And this overall means that the lambda is lower. At least that's our explanation for it. But the color code uses fewer qubits to get to the same distance. And so maybe just looking at lambda isn't quite the fair comparison. If I had a device and it has a certain number of physical qubits, what's the best I can do with that device? Well, if my color code uses fewer physical qubits, but I have all that space, I'll go to a higher distance. So let's compare surface codes and color codes by qubits used, not by distance, because I said that's not fair. And what we found was, there's a question about decoding. This is actually using a maximum likelihood decoder based on integer programming. So not fast enough for real time, but very accurate. And we found this interesting effect, which is the yellow lines are the color code, the superdense is the style that we implemented, and the blue lines are a surface code. And we ran simulations. This is all simulated data with different error rates. And we said, well, what happens as you increase the number of qubits? Each point is a different distance, but they're not on top of each other because the color code and surface code use different numbers of qubits for the same distance. And so there's this really interesting effect that I think is the first time this has been reported, although maybe, I don't know, it's the first time I've seen it, that the color code, when compared in this way, appears to overtake the surface code. And in some sense, you could probably argue this is inevitable, that the fact that it uses fewer physical qubits means that at some error rate, it will have an advantage. But we showed that this is pretty close to where we are today. This is like a factor of maybe 3 or 4 from the error rates we have in our current devices. So there's this possibility that maybe color codes are a better code. I'm not going to say the story's over. Lots of work to do, lots of things to study. But it is kind of interesting to see that scaling up, even if the lambda is a little bit lower, it's not everything. It's really like what's the utilization of the resources in your system. And color codes seem to be pretty compelling, at least worth further study. So I have some discussion questions. I know I'm kind of at the end of time. Should I just go through them anyway? Yeah, okay. Were there any questions from the audience? Yeah, go ahead.
Are like higher dimensional color codes expected to be better than lower dimensional color codes?
I don't have a short answer for that. They have distinct properties. If you have a system that can implement the 3D connectivity that you need, then they're very attractive. They have a property known as single-shot error correction that makes them particularly resilient to stabilizer measurement. But there was that requirement that you have a system that can implement them. And so superconducting qubits do not have a simple path to implementing 3D connectivity.
So the number of swaps needed to actually map it onto a plane would just be prohibitive?
Yes, and it would be a penalty that increases with distance, right? Yeah, I think they're interesting, but it really depends on the architecture you're running them on, whether they're worth or whether they are attractive. Okay, discussion questions. How can you tell that leakage removal is working? Yes. It's what? Okay, yeah, that's definitely one way you can tell. Any other additional answers or alternative ways you can see that leakage removal is working? Yeah.
Value of lambda increased, right?
Yeah. Yeah. Okay. So 2 different ways of comparing this. First is by directly measuring leakage populations and showing that leakage is going down. And second way is that by running an error correction experiment, showing that leakage removal is beneficial. All right. Okay, what are the reasons for the real-time decoding experiment? This is a fun one. What are the reasons for the real-time decoding experiment to go to 1 million rounds when the logical qubit only survives for maybe 1,000 rounds? So there's an arrow pointing to the limit of this plot was 250 cycles. So why did we go out to 1 million cycles, even though the logical qubit is no longer holding useful information? Yes.
The clock time, the wall time of the errors might not be large enough to see the scaling at long cycles.
I think I agree with you. The issue is you want to make sure that your decoder is always keeping up, that there isn't some sort of like, it works at short experiments, but then at some point it's like building up a backlog. Things you might worry about. The decoder not meeting throughput. So that means that the decoder is running slower. And if you ran a short experiment, the fact that it's a little behind isn't obvious. You have to keep increasing the number of cycles to stress the decoder and show that it really is always streaming information through. And kind of related to that, you might worry about resource limits. I said this runs on a computer. Computers have limitations. Could be filling up a communication buffer. We have to get measurements from FPGAs into a server, into a workstation. Several stages there. Or you just might worry about running out of memory. There's only so much RAM you can have. There's examples. And then finally, something you might worry about is rising error rates in the quantum processor. We can independently verify that the error rates are stable up to 1 million cycles. But, I said the decoder is sensitive to the error rate, and you kind of want to just double check that everything is stable. All right. What qubit connectivity is required for the color code?
Nearest neighbor.
Oh, sorry. I don't know, do people want to shout it out, or anybody? Oh.
I think it depends on the technology used. For example, if you use a flag bridge for the syndrome measurement, you can lower the qubit connectivity. For example, in your experiment, you show the color code on a square connect graph, but in ideal, if you want a triangle grid, but with a flag bridge technology, you can lower the requirement for the qubit connectivity.
I'm sorry, what was the technology?
Flag bridge, or if you, or the same, it's like the same you showed in the in the picture. You use 2 syndrome qubits or 2 ancilla qubits for one stabilizer, so it lowers the connectivity requirement. And a flag bridge is something like that. You use a flag qubit to enlarge the syndrome qubit, so you can enlarge you can connect with the syndrome qubit with more data qubits.
Okay, a nuanced answer. I like it. There are several implementations of the color code, and you actually described a different one that's possible. But we showed that the 2D square grid was sufficient for running a color code.
So 4. The connectivity 4 neighbors is enough.
Yes.
Yes.
Yeah, a square grid meaning nearest neighbor connectivity in a square grid. Yeah.
Can you go down to like a honeycomb type of a heavy hexagon?
As this gentleman was pointing out, there are graphs with 3-way connectivity that would support color codes as well, so-called trivalent, I think they're called trivalent graphs. There are trade-offs. So having lower connectivity means you have to build larger resource states to measure the stabilizer. So you can see here, if I have a 2-qubit resource state in the middle of my tile, then in this connectivity, that has 6 neighbors, right? this guy has 3 other neighbors, this guy has 3 other neighbors. If you had say a trivalent graph, you would need at least 3 qubits here in the middle. Maybe it's more than, I have to think about that, but more than 2. So there are trade-offs for different connectivities. Okay, well, that is the end of my talk.